Welcome to a new video. So in the last video, I think we discussed about subnet and how they work, and also we discussed about like why do we need IP addresses and stuff. But before diving deep into, I was thinking of going deep into IP address actually, but before diving that, I thought it would be a convenient thing to like take a top-down approach. So I thought of starting with like TCP and IP. So that's why we'll be discussing TCP in this video in a bit of detail. Like there are many jargons and stuff, but ignore them for now. We'll go through them one by one eventually, slowly. Yeah. So a quick recap from the last video. Like why do we need IP addresses? We discussed this. Basically, the main problem was we couldn't have just the MAC as the identifier, because finding something would be a disaster. Finding any device would be a disaster if that were the case. So IP addresses were introduced to make the communication faster, so that it's easier to find the device on the other end, and that being the primary reason of it. Subnet being something that would help you to identify if the device you're looking for lies on a particular network, and if it lies in the network, then it's somewhat called the device lies in X network subnet or that sort of a thing. So those are pretty straightforward, I think. Like if you have any questions, you can always ask in the comment section. That's not an issue. Now let's move on to TCP. As we discussed in the OSI model, again a quick refresher. If we assume this to be a person, like if you haven't watched the video, you can watch. I will link it somewhere around here, I think. Yeah, basically. But a quick refresher, like if you were to talk to another person or another device, what we came into agreement was we need suppose there are two people who talk in two different languages. We would need a translator, common translator between them, which could encrypt and which could communicate what each person is trying to say to one another. We would need some context for the conversation to take place, which is then the session layer as discussed, and to maintain it throughout the conversation, and we need to end it sometime, so then the session or the context will be destroyed when the conversation ends. Then we need 3 layers of packaging, and then we just transport it. We talked about all of them in detail in the the OSI model video. You can just go and watch that if you want to, if you haven't watched it yet, or if you want to go into depths of it. But yeah, now let's move on to TCP. So what is TCP? TCP refers to transmission control protocol. Here the word control has like a huge significance, because when we'll discuss UDP, you will know that we will realize the significance of the control. But just for the sake of it, I'm saying it now. Like basically, it's when we say control, like it has a significance. That's why the word is there. So we are it's same as what it says. We are controlling the transmission. We have the control of the whole transmission. In UDP, that's not the case. When we will go to it, we'll discuss that. But just remember this for now, that the communication is controlled in TCP. Like it has a particular beautiful flow that will take place, connection established, and the whole communication takes place, then the connection is closed. It's like everything is taken care of, and it's like in a very elegant manner. So that's why we have the word control there. So yeah, let's get started. So here, as we discussed in the OSI model video, in the transport layer, we deal with TCP and UDP. We are discussing TCP now. So anything related to TCP, data or whatever, like it's called segment and datagram respectively. For UDP it's datagram, for TCP it's segment. And the part of the address that we discussed, that's taken into consideration while in the transport layer with TCP and UDP, is the port. So that's an important thing. Now, if you can see here, that's the first point basically. TCP deals with ports. Like if you were to communicate between application to application, that thing would be mostly taken care of by TCP or UDP. The application part of it, rather than routing and everything, it just mostly it focuses on the application part of it. It assume that you have reached the device. Now which application you want to talk to, that will be mostly handled by TCP. So then we have more control as in more is a relative term, of course, and you will get to see the bigger picture when we discuss UDP. But yeah, it's basically the thing that we discussed initially. Like the whole flow is very elegant. like as if a real conversation is taking place between two people, and how it would take place. It's like similar sort of a replication is done here also. Like it's very elegant. Then we have context and connection. This is an important thing. We discussed about context and connection in the session layer. I think like it's the responsibility of the session layer to maintain the context and the connection throughout the whole conversation, or throughout the whole thing that the data goes back and forth until it's closed. Then yeah, these three things are clear, I guess. We already discussed these things once, so I'm not going very deep into it. Basically here I'm referring to as we discussed, like there needs to be some context for the conversation or the communication communication to take place. So that's being referred here. Stateful. This is a new word. Stateful and stateless. These are two things that we'll get to hear very often. Stateful is like it needs some initial information for it to operate in the first place. Like here, let's say you won't be able to communicate, like send data for TCP and stuff without the connection and stuff. So there is a state that is maintained throughout the whole process of communication. So that's the so that's why stateful. There needs to be some context, there needs to be some connection, there needs to be some kind of a thing, so that we don't have to send everything over and over and over again. So that's mostly that's why it's called stateful, because there is some context that is associated with the whole connection. So whenever we are sending some data, we don't need to send all the details associated with it, since we already have some context from before. We can use that. Then we have reliable. Reliable because we will know, like we said, it's a very elegant flow. Like the way connection is established, the way data is passed, and the whole communication takes place, it's very elegant. So when you are using TCP, it's mostly like a guarantee that you will you will get the data the way and however it was intended to be. So it's very reliable, unlike UDP, which does something else, but we'll come to that. Again, it's bidirectional. We discussed about HTTP once, I guess I mentioned it. In HTTP, what happens is, like, the communication is not what to say. Yeah, I mostly explained the OSI model in an HTTP sort of a thing only, assuming that it's an HTTP, because we said that like it will send something to them, they will send something back to this, and again it will go through. Like, it's not bidirectional, if you see, because basically when it's sending some data, it's waiting for your person to send something back, then it will send again. So this is called a request response format. So person 1 is making a request, person 2 is responding, 1 is again making a request, 2 is again responding. But with TCP, even without receiving the data from the other end, you can send more. There is some limitations to it, of course. We'll come to that. But yeah, basically you can keep sending data without waiting for the other side to say something. Assume like a situation, like just keep the framework of basic communication in mind and try to understand it. Basically, suppose you are speaking, you are not necessarily you need the other person to reply to everything. You spoke something, you can speak again without waiting for, like, without receiving the reply or waiting for it, basically. But yeah, you cannot push it too far because it has its limitations. Same as in real life, like you cannot keep speaking without hearing the other person. So it has its limitations here also. We'll come to that. But that can be done. That's the basic point that I wanted to convey. Now, how the connection works. We have been talking about context, we have been talking about session, we have been talking about connection. Now it's time for the holy grail, like how does it actually work? I mentioned it. Okay. So there is something called three-way handshake. So there is something called three-way handshake. So let's say you are device 1. You want to establish a connection with device 2 for maybe assume these two are people and they want to talk to each other. You can assume that as well. So this is device 2. So forget about everything. Just imagine it's a real life scenario. How would device 1 go ahead and communicate with device 2? So let's assume a conversation. Device 1 would approach. He would be like, yeah, hey device 2, how are you? Then maybe device 2 would be like, yeah, I'm doing fine, how are you? So device, if I can just, damn, this thing is annoying. Okay. So device 1, like it will ask device 2, hey, how are you? Then device 2 would respond with something like, yeah, I am fine, how are you? So device 1 would respond with something like, yeah, I am fine too. Can you just tell me about this? So from that point, the conversation starts. Like the initiation part takes place. Initiation is that how are you questioning and stuff to just initiate the flow of the conversation. And after that, the actual conversation takes place. And like whenever it's done, it's completed. We'll come to how it's finished, but that's the establishment part of it. How are you? I am fine. How are you? I am fine too. Let's talk about this. That's all. So these have some specific terms that we can map them to. Let's say, yeah, basically these are just fancy terms to represent whatever things we just discussed about. It's called SYN. Let's say when device 1 is asking how are you, in technical terms what you would say is it's basically sending a SYN packet to device 2. Device 2 is answering the question and asking back how are you again, like I am fine, how are you? So basically device 2 is answering or acknowledging the question and then asking again, like, okay, I am fine, how are you? So again another SYN slash, I think, yeah, this should communicate it well. Device 1 does SYN, sends SYN packet. Device 2 sends an acknowledgement along with another SYN. Device 1 sends acknowledgement, I am fine, with the response, and then the connection is established. So this is how the initiation takes place. Like I said, it's very similar to how we do it in real life. These are just technical terms that are introduced, which makes it very confusing to understand, but it's nothing that complex in actual. So basically the same thing. Hey, how are you? I am fine. How are you? I am fine. Let's talk about this. That's what. After this, the data would just flow through until the connection finishes, which we will come to eventually. Now that we are aware of how the connection takes place, let's talk about how data is transmitted. Like first step is connection. Remember these three things. First step is connection. Second step is data transmission. And after the data is transmitted, third step is closing the connection. These are the three very elegant steps that we need to take into consideration in a TCP. For UDP, it's nothing. Like we'll come to that. But for TCP, when we say control, we mean these three things: connections, data flow, closing the connection. Opening the connection, data flow, closing the connection. These three things you just need to keep in mind. Now we come to segments. So basically, let's say you have some data that you want to send to device 2, but you cannot send them all at once, maybe because of some size issue, maybe because of how much device 2 can handle at once. For whatever reason, you cannot send it like that. So you divide them. Basically, imagine you have a huge set of data to send, but device 2 cannot consume all of it at once, maybe due to some limitations. We will discuss those limitations. Those are called flow control and congestion control and stuff, but we'll come to that. But let's assume device 2 cannot take in the whole data at once. So we divide them in pieces and send them one by one. So then it's called segments, or like data is basically segments, as you can call. The data is segmented, and it's segmented in sequences. Like it's segmented in sequence. Like there will be a serial number associated with every data. Like this is the first piece, this is the second piece, this is the third piece. So that on the other side, device 2 can collect them and rearrange them and read the data in the accepted format. Like let's say device 1 wants to send data 1, data 2, data 3. Let's assume these are the segments. Let's add another one, data 4. Let's assume these are the 4 segmented piece of data that we want to send. These will have the serial numbers, as you can see, data 1, data 2, data 3, data 4. These are sequenced. One thing that you need to keep in mind that will device 2 receive the same data in the same sequence as device 1 send them? Will it? Like we discussed, it's bidirectional. It's not request response format. Like device 1 won't send data 1 and wait for device 2 to say, okay, I received data 1, I send the other, like send the next one, because that would result in extra overhead. Like see, assume the time that it would consume if we were to wait for device 2 to send it back, and 4x it for 4 segments of the data. So that's an issue with that. So we cannot do that. Like we can just burst them out and device 2 can just communicate when they receive it. There is a procedure that is done with, but the question is, will device 2 receive the data in the same sequence as it sent? And the answer is no, of course not. Imagine device 2 lying in some other corner of the world and it's like getting routed through thousands of routers. You cannot guarantee that data 1 would receive device 2 before data 2. It might be the other way around. There is a possibility of that. There is a possibility of data 1 being lost also. Like device 1 sent data 1 but device 2 never received it. That's also a possibility. So now what we would do? But we also need to maintain this bidirectional thing. We cannot wait for device to respond back because that would cause extra overhead on our side as well. So now what we do is, let's say we send all of them. Let's say we are sending data 1, we are sending data 2, we are sending data 3, and let's say device 2 received it. As of now, we haven't sent data 4 yet. We have just sent the first 3 packets. First 3 segments, not packets. We have sent the first 3 segments. So when device 2 receives it, it will send an where do I connect it? Let me connect it to device 1. Yeah. When it receives these 3, it will send an acknowledgement. Acknowledgement is something that you refer an answer to as, like when any of the devices answering, you can call it an acknowledgement or answer. Like basically acknowledgement is like, yeah, yes, I received it. So it will have a reference to the last segment that it received. So let's say data 1, data 2, data 3 was transmitted or sent from device 1. It would send an acknowledgement with reference to data 3. Like it's basically saying that, okay, you send data 1, data 2, data 3. I receive till data 3. I won't send one acknowledgement for every one of them, but I'll send for the last one in the sequence. Since they are sequential, it would automatically mean that like above data 1 and data 2 are received, since the acknowledgement is associated with data 3. Since they are sequenced, keep that in mind. Like there won't be acknowledgement for every single one of them. There will be acknowledgement for the last one in the sequence, whichever device to received. Now device 1 is like, okay, you received till 3. Now can I send 4 over? Then he sends 4 over. Data 4 is sent over. Then device 2 again. I'll just do it in sequence so that it's easier to understand. This will be okay, this will be here. Now data 4 is sent, and after 4 is received, device 2 would acknowledge that as well with ACK with reference to data, data 4. Yes, if you spoke it right, congrats, you understand it, you understood it. So that's the whole flow. What you need to remember is data is divided into, let's summarize the whole thing. Data is divided into segments. Segments are sequenced. Sequence segments are sent one at a time, but we cannot guarantee device 2 to receive all the sequence in that particular order, and data can also get lost in between. We'll come to how to handle that, but let's assume like for this use case, let's assume all the data that were transmitted were received by device 2, not necessarily in order, it can be in different order also. Then how device 2 would say to device 1 that I have received these 3 pieces of segments. It will just send an acknowledgement which will be in context to the last piece of data that it received. Since the whole thing is in sequence, device 1 would know that if it receives acknowledgement 3, that is something related to data 3, it's clear that data 1 and data 2 also was received because it's acknowledgement 3 and it's sequenced. So if they receive 3, they also received 1 and 2. Since the acknowledgement is always sent with the most recent data that it receives and which lies in the bottom of the sequence. So that's what. So basically when it sends 3, it means that it receives 1, 2 and 3. If it sends 4, it means it receives 1, 2, 3 and 4 and so on. Basically it won't send one single acknowledgement for every single segment. That's the thing that you need to keep in mind. That's a bit tricky, but I think it should be clear by now. I said it like 1,000 times already. Then data 4 would be sent. Once data 4 is received, device 2 would acknowledge it and send acknowledgement for that data back as well. Now let's assume data 3 got lost somewhere. Let's say device 1 sent data 3, of course, but device 2 never received it. Now what would happen? Let's say it got lost in the void of the big internet somewhere. Now what would happen? Because if it were to consume data 4 without data 3, it would have to like order them in a manner and the data would be corrupted. Since one piece of the data is missing, the whole packet, the whole data would be useless because it won't be able to reorder them and get them in the actual format that it was sent. But we call TCP reliable for a reason. Here is why it's called reliable in the first place. There's a lot of things. So like we assumed, it's a similar thing. Basically device 1 sends data 1, data 2, data 3. Device 2 received data 2 and data 3. Data 1 and data 2, but didn't receive data 3. What would happen? If you can take a guess, device 2 would send acknowledgement associated with data 2. Yes, acknowledgement associated with data 2. Since it never received data 3, it receives just data 1 and data 2. It's like, okay, I received till data 2, but whatever is after that, if you have sent it, I haven't received it, so you need to send it again. So device 1 is like, I sent data 3, but maybe device 2 didn't receive it. Since it only sent acknowledgement 2, that means it received till 2. So I'll retransmit 3 again. So what it would do is, it would resend it. Since the old packet was lost, it would resend it. And again, it would maybe resend data 4 altogether. Then again, it would acknowledge with acknowledgement 4. So ACK 4 means basically it received everything till data 4, 1, 2, 3, 4 in sequence. That's all. So that's why it's very reliable and it's mostly guaranteed that the other end would receive the data. But of course, the drawback is like you need to maintain a connection while this whole thing takes place. Because if there is no connection and you try to send data, those packets will be dropped like immediately. Like here, as we mentioned it, without connection, data is dropped. I keep saying packets for some reason. Like basically, packet is something that associated with IP addresses, so I don't want to mix that up. Basically, without connection, the data is dropped. Like it won't accept it if it's not reliable or if it's not from a reliable source or if there is no connection. Like let's say in real life you can compare it to some situation where some unknown person tries to talk to you and you're like, I don't know you, like why would I talk to you? Similar kind of a thing. If there is no context, the conversation won't take place and the data is dropped. As simple as that. Now I think we discussed TCP handshake. This is called TCP, three-way handshake because 1, 2, 3. As simple as that. Like data, like there are 3 flows that take place for the connection to take place, and that's why it's TCP handshake. Three-way handshake. Yeah, that's why it's called three-way handshake. Or basically there are 3 flows that take place. As simple as that. You can remember it like that only, nothing complex. So then we have I think we discussed this. Yeah, can send before waiting for acknowledgement, like we discussed. Here we aren't waiting for acknowledgement for data 1. We are just sending data 1, data 2, data 3 together. And device 2 would respond with the last data in the sequence, and it just needs to send everything after that again. So we are not waiting for the acknowledgement for every piece of segment that we're sending. Lost ones are retransmitted, which we also discussed with data 3. Like maybe data 3 is lost, it will acknowledge that it received till data 2 with act 2, and then again data 3 would be retransmitted like we discussed here, or it's written here. Now if we talk about the connection framework, see, basically connection framework as in these data things that we are talking about, how it would reach device 2. Like we discussed in the last video, it needs an address to reach. Like we cannot just send the data over and like it would be reached. So to establish the connection and everything, and to transmit the data overall, we need source IP address. Let's try to recall when we discussed IP and ports and connected them to a framework of landmarks and house numbers in real life. Compare it to that. We need the source IP address, we need the source port, IP address for the device, port for the application. We need the data and everything, whatever you're putting it here. It can be CNAC package, it can be whatever data we are passing it through. We need the destination port, we need the destination IP for the destination application and destination device. You can think of it that way. Because one device will have multiple applications running, you need to target one particular application. So that's why we need the destination of it as well. Now we are done with opening connections, we are done with the conversation. Now we need to close it. Basically it's like saying farewell. Okay, I'm done talking to you, now I'm leaving, and so on. So how would that take place? Basically saying farewell to each other. Just remember these three things. For a connection, it's SYN, SYNAC, ACK. For closing a connection, it's FIN, ACK, FIN, ACK, time wait. It's a thing, like even it rhymes properly, so it's easier to remember. But yeah, let's draw a new diagram for this. It's getting too cramped up. Device 2, I'll just move away from, okay, diagram. Yeah, basically now let's say we are done talking to device 2. We are done with the data transmission, everything. Now we need to close the connection. So what we would do, like we said, it's very elegant. It will open the connection, it will proceed with the transmission of data, it will close the connection. So it's very elegant and it's very reliable, and you can almost guarantee that whatever data you send, the other end would receive it no matter what. So yeah, it's very reliable. That's what I'm saying. Again and again, I think. Yeah, basically let's say device 1 is done and device 1 wants to end the connection. So like SYN, it would send a FIN request. Let's copy this and paste it here itself. It would send FIN. And if device 2 wants, if device 2 wants to end it, device 2 would also send an acknowledgement for the FIN. Like, okay, let's end this thing. Then device 2 would send, then device 2 would itself send a FIN. Like, let's end the connection. Now device 1 would acknowledge this FIN. Like, I'm putting it in a proper sequence on how it would actually take place. And after that, there is something called time wait. Like once device 2 is done, like see, basically device 2, here we send a FIN, device 2 acknowledge that, okay, this connection, I want this connection to be closed. But after it's done transmitting the data, it would send a FIN, the next thing that it would do. Because it may be something like when device 1 send a FIN, it may be transmitting some data. So on acknowledgement, we cannot close the connection. Device 2 has to also agree that it's ready to close the connection. So basically it says, okay, I acknowledge it, but give me some time. I will also send a request to you to close the connection. Then we would proceed. So basically it's a two-way thing. Here, this wasn't the case because there wasn't any data coming from either sides. But here, let's assume device 2 is sending some data, and if we just in that time close the connection, data would be lost. So basically what's done is device 2 would acknowledge the fin, and then when it's ready for closing the connection, it will send the fin on its own. Like, okay, now I'm done sending everything, now we can close the connection. And device 1 would acknowledge that. But here again, the case comes up. Let's say device 2 is done sending the data, and device 2 sends a fin to device 1, and device 1 acknowledges the fin and closes the connection immediately. But in the physical world, in the wide internet, we cannot just close a connection like that, because there can be many packets that are sent by device 2 but haven't reached device 1 yet. If we close the connection, like let's say device 2 sends some data, device 2 sent 4 segments, let's assume we receive 3 of them, and then we receive the fin, and then we receive the 5th segment. Let's say I'll just draw it down so that it's easier to visualize. Okay, so let's say device 2 send data in this sequence and also the fin, but device 1 received it in this sequence. Like let's say the fin was sent after this from device 2. Device 1 received it in this sequence. This is sent, this is received. Just keep that in mind. I'll just draw an arrow as well for it to be clear. I'll just put it in a box, I think. Okay, let's do that. Let's put it in a box. Yeah, so this is the whole thing that device 1 receives, and this is how it's sent. Sorry, I'm taking a lot of time, but bear with me. It's gonna be worth it. Yeah. So this is the direction that data flow is happening. It sends data 1, data 2, data 3, data 4, and then it sends the fin. But since routing and everything takes place, and maybe the 2 devices are sitting on other corners of the world, it receives data 1, data 2, data 3, fin, and then data 4. So imagine device 1 closes the connection as soon as it receives fin by sending an acknowledgement. It will never receive data 4, and if it never receives data 4, it cannot reconstruct this whole data, because this is the same data that's broken into segments, and then for it to be valid or for it to be used in the expected format, the whole data needs to be intact. So what it would do is, there is something called time wait. Okay, there is something called time wait. So the device that initiates the closing of the connection, as in like sends the fin first, will wait once it sends acknowledgement for the connection. After the whole 4-way handshake takes place, it will wait for some time. It will keep the connection open for some time, so that any data that's in the internet which was sent by device 2 to internet for device 1, that doesn't get lost. And after some time it would close. Like there is a buffer time for waiting for any lost data. Even after it acknowledges that okay, I'm closing the connection, it will wait for some time, so that data 4 in this case doesn't get lost, and it receives it, and then it can reconstruct the whole thing, and it would be used however it's intended to. So that's the reason the connection won't be closed immediately. It will be closed after some time. The device waits, and then it's closed. So that's a thing that to keep in mind. So yeah, I think we discussed a lot of things here. Okay, to summarize the whole thing, TCP deals with ports. We have more control in TCP. We need a connection and context. It's stateful, because there is a connection and context that is maintained throughout the whole communication, so that we don't have to keep sending data. We don't have to keep sending everything associated with it, since we already have some context and connection associated. So it's stateful. I mean, it has a maintained state. That's all. It has a maintained connection. It has a maintained state, whatever you call it. Stateful. It's reliable. Reliable because when you send something, it's almost guaranteed that the other end would receive it. It's bidirectional. Bidirectional because it's not the request response format like we discussed. Device 1 would say send something, device 2 would send something back, then again it would send something, because that brings up that initial waiting time in between. So it can just send without waiting for the device to send like data for whatever it sent initially. It can just send data 1, data 2, data 3 all together. It doesn't have to wait after sending data 1 that, oh, okay, you received it, now let me send the other one. It doesn't have to do that. It can send them all together. So that's why it's bidirectional, and same device 2 can do it device 1 also. So yeah, it's not like request response HTTP format sort of a thing. Now, how TCP connection works, as we discussed, the TCP handshake takes place. It's a three-way handshake that we call the SYN-SYN-ACK ACK. Hey, how are you? I am fine. How are you? I am fine too. Hey, let's like talk about this. That's all. As simple as that. Then we have segments. Since data is like maybe device 1 has a lot of data to send, it cannot send them all together at once. So it breaks them down and numbers them in serial numbers, like this is number 1, this is number 2, this is number 3, so that on the other end it can be arranged in the proper order and consumed properly as it's intended to. So that's mostly segments, and that's how data is sent if it's a very huge chunk of data. And can send data before waiting for acknowledgement, like we discussed. It can send data 1, data 2, data 3, everything all at once. It won't send data 1 and wait for the acknowledgement for data 1 and send data 2 and wait for it and so on. So it will just send them together. So it won't wait for acknowledgement for each device. In this way, the communication is faster, if you can imagine. Otherwise, we'll have to wait. If you were to wait for every single data before acknowledgement for every single data before sending them, that would be a disaster. Like it would be very slow. It's already very slow due to this connection thing and connection breaking thing and everything. We don't want to add any more overhead to it. So yeah. Lost ones are transmitted. Like, why does this keeps on happening? Yeah, lost ones are retransmitted. So whenever data is lost, device 2 would notify with the last serial number of data it received. And if it's not the same as the data that was sent by device 1 the last time, it would retransmit it. Basically, device 2 is saying, hey, I received, device 1 sends still data 3, device 2 sends acknowledgement 2, as in, hey, I received data just till the second serial number. I didn't receive anything after it. So device 1 would retransmit 3. Even if it sent 3 initially once, it would retransmit. So that's what I mean by lost ones are retransmitted. Connection framework, like we discussed, landmark, house number, whatever parcel or order you want to send, house number, landmark, that's all. There are many other layers before it. We'll come to that later. But yeah, basically source IP, destination IP, source port, destination port, data. It can be anything. It can be some data that you are sending throughout the connection. It can be the SYN-ACK thing. It can be anything. Then we have opening connection, three-way handshake, SYN-SYN-ACK ACK. Closing connection, four-way handshake, like we discussed this thing. FIN-ACK, time wait. Done. So this is the whole TCP thing. Not that complex. Very simple. If you try to associate it with real life, it's very simple, as I said. So yeah, it's a very long video. I think it's almost 40 minutes now. Probably the longest video I've made till now. Yeah, that should be it, I guess. Next we'll discuss something new. It's a long video, so if you have any questions, you can always ask in the comment section, and I'll try to answer. I will answer all of them, of course. Yeah, so yeah, see ya guys, good day.